Okay, so we're starting a new unit, Unit 3, Periodic Table. And tonight's lesson is going to be kind of quick because, well, it's going to be quick in the sense that I'm going to be reviewing some stuff that you already know, so I'm going to fly through that. And then there's going to be a lot of new stuff, but I'm just going to try to give you a broad taste of what we're going to be discussing in this unit, and then we're going to go back and reinforce that through several lessons this week. So what we're going to accomplish in this lesson is we are going to discuss the origin of the periodic table, what we mean when we discuss modern periodic law, how an element's placement on the periodic table is related to its electron configuration, and lastly, what are some general characteristics of various groups in the periodic table. So let's get started. You should have your new packet in front of you. So Dmitri Mendeleev developed the first periodic table, and he arranged the elements according to ascending atomic weight. And he grouped elements by similar properties. So when we talk about properties, maybe, how they looked, their texture, whether they were shiny or not, that type of thing. And he predicted the existence and properties of new elements based on how he put them into their groups. And what he noticed is that there were gaps and how few elements there were. So you can see in this crude design of the periodic table, here are the different groups he had. So he had helium and neon and argon in the same group, and krypton and xenon. So all of those were noble gases. And then he had lithium and potassium and rubidium and cesium, so that's kind of similar to what we have. And then fluorine, chlorine, but manganese certainly isn't in the same group as fluorine and chlorine. And then here's bromine and iodine, so some of the other halogens. But when he did this the way he did according to atomic weight, he noticed that he had all these gaps. So, but it was a very good beginning. I don't want to discredit Dmitri Mendeleev. But what Moseley did was even more important. He was an English physicist who determined the number of positive charges in the nucleus by measuring the wavelength of X-rays given off by certain metals. And he developed the first concept of atomic number. And that is what we know it today. Atomic number is how our periodic table is arranged, and it also represents the number of positive charges in the nucleus. So periodic, the word periodic in itself means cyclic or repeating patterns, similar to a monthly or weekly calendar, days of the weeks. Example, tired on Monday, happy on Fridays. So let's review the two of those. We just discussed them. So Dmitri Mendeleev, he was the first chemist to arrange newly found elements into a table, and he arranged them according to atomic weight. This resulted in gaps, or the periodic table being out of order. Henry Moseley came along and arranged the table by atomic number, or number of protons, because that's basically what it is, which proved to be much more effective, and it's also how the modern day periodic table is arranged. And that brings us to periodic law. Elements in the periodic table are periodic functions of their atomic number. So by grouping elements by their atomic number, they fall into these groups that have similar characteristics. And we are going to discuss what those characteristics are in just a little bit. The periodic table is made up of periods and groups. Periods are horizontal rows which run left to right. The number of the period tells us the number of principal energy levels. And in parentheses, you can say electron shells. Properties of the elements change drastically across a period. So when I go from left to right, they change drastically. We go from metals to metalloids, or semimetals, and then to nonmetals, and then to noble gases. The number of valence electrons increases from left to right, from 1 to 8. So let's look at this a little bit. Down here, I have copied period 3, which contains sodium, which has an electron configuration of 281. I'll write it a little bit bigger if you don't have your table out. So period 3 tells me that there are 3 principal energy levels. Here they are. This is the first principal energy level. This is the second principal energy level, and this is the third principal energy level, just as we discussed in the last unit. Period 4, potassium, is 2881. So it has 4 principal energy levels. So what the period number tells us is that every single element in period 3 all have 3 principal energy levels. All the elements in period 4 all have 4 principal energy levels. Now, we also know that everything in group 1, if we look at everything in group 1, they all end in 1. They have 1 valence electron. In group 2, magnesium is 282. Calcium is 2882. Everything in period 2 has 2 valence electrons. So that's what this last statement means. Valence electrons increase from left to right, 1 valence electron all the way to 8 valence electrons. So when you get over to this last group, group 18, argon is 288, 8 valence electrons. Chlorine is 287, 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. We don't count the transition metals, groups 3 through 12, when we talk about valence electrons. They're special. We'll deal with them differently. So group 1, 1 valence electron. Group 2, 2 valence. Group 13, 3, 14, 4, 15, 5, 16, 6, 17, 7, and 18, 8. Okay, groups are our vertical columns. Meaning that they run up and down on the periodic table, and each group contains the same number of valence electrons, as I just showed you. And similar, not identical chemical and physical properties. So let's just look at the electron configurations. I'm not going to do Lewis dot. I'm going to look at the electron configuration so you can see the trend. H, the electron configuration, I'm giving you electron configurations, is 1. Lithium is 2, 1. Sodium is 2, 8, 1. Potassium is 2, 8, 8, 1. Rubidium is 2, 8, 18, 8, 1. Cesium, 2, 8, 18, 18, 8, 1. And francium is 2, 8, 18, 32, 18, 8, 1. What do you notice about all of these? Hopefully that they all end in 1. So if I were to draw the Lewis dot structure for any of these, 1, CS, 1, francium, 1, they all have the same Lewis dot structure. What similarities can you observe within the above electron configurations? Well, we just said it. They all have one valence electron. Group number equals the number of valence electrons, as I showed you a couple slides ago. The period number equals the number of principal energy levels, or electron shells. And an octet, oct means 8, is full valence or 8. 8 electrons except for period 1 elements. And there are 2 exceptions in period 1. We have hydrogen, which only has 1 valence electron, so it's just 1, and helium, which has 2 because they're so small. All right, let's briefly discuss some of the groups and we will be done. So group 1 is known as the alkali metals, and they all have 1 valence electron. They easily lose their 1 electron to become +1 ions. So what that means is they have 1 more proton than electrons. So when you have more positive charges than negative charges, you have a net positive charge. They are extremely reactive. If you recall, I showed you a YouTube video on alkali metals with rubidium and cesium when they blew up the bathtub. Extremely reactive. They're never found alone in nature. So what that means is that they are usually found bound to a halogen, which is group 17. So normally we find them bonded to either maybe chlorine, fluorine, bromine, or iodine. Contains the most reactive metal, which is probably francium, which is Fr, but it's so rare we also have to go with cesium. And then we have the alkaline earth metals. They all have 2 valence electrons, and they prefer to lose their 2 valence electrons to become +2 ions. So let's just take for an example 282, which is magnesium. Remember, I said that everyone wants 8 in their valence shell. So you have to look at the valence shell and say to yourself, is it easier to lose 2 or gain 6? So in this case, it's easier to lose 2. And then it'll have 8 in its valence shell. And when it does that, it's now got 10 electrons and 12 protons, which gives it a net +2 charge. They're fairly reactive. and never found alone in nature. So they're also found bound to something. Groups 3 through 12 are our transition metals. They're found in the middle of the periodic table. They're also referred to as the D block, and I'll explain that to you in class on Tuesday afternoon. This is extremely important and always a Regents question. They form colored ions in solution. And they tend to be unpredictable, meaning that they can either gain or lose electrons depending on what they're hooking up with, or what other metals are present. Same as hooking up with. And they are the least reactive group of metals. And then we have groups 13 through 16, and they're not a group. They're just referred to as BCNO because that's what they start with. Boron is group 13, carbon starts group 14, nitrogen starts group 15, and oxygen starts group 16. So 13, 14, 15, and 16. So they're kind of on their own out there, and they are referred to as miscellaneous groups. And they have metals, nonmetals, and metalloids found along the staircase with many different properties, which we're going to go into more depth, but for right now we're just doing an overview. 17, the halogen family. They have 7 valence electrons, and they like to gain 1 electron so that it will have 8. So if they gain 1 more electron, that means they're going to have a -1 charge because they'll have 1 more extra electron than proton. And they like to form salts, other various compounds, and they are called halides. And they're going to come up not just now in this group, they'll come up in bonding, they'll come up in organic. And they contain the most reactive nonmetal, which is fluorine. And they contain all 3 states of matter. The 3 states of matter found in the group are solids, liquids, it's an L, and gas. And for examples, we have fluorine, which is a gas, and we have chlorine, which is a gas, and we have bromine, which is a liquid, and iodine, which is a solid. And on Tuesday, I'm going to show you how to use Table S to determine that. And lastly, Group 18. Those are our noble gases, and they are the most unreactive, or what is called inert group. They already have an octet. I got ahead of myself here. So they already have an octet, which is 8 electrons in their valence shell. They're the most stable group on the periodic table, and they basically exist alone in nature. They don't want anything from anyone, they don't want to give up, they don't want to gain. Exception to the rule is helium, which only has 2 valence electrons. everyone wants to be a noble gas and have 8 because 8 is great. And an example of that would be neon, Ne2, 8. So when we talk about bonding in a later unit, you're going to see that elements will either give up electrons or gain electrons in order to get 8 in its valence shell. Hydrogen is not officially part of a group, even though it's listed above group 1. It is both a nonmetal and a gas. And can be seen as H2 because it's diatomic, part of Brinkelhoff. H plus aqueous, and you'll learn more about that when we talk about acids, or even H minus aqueous. Okay, and that's it. Have a great night.